Hello, everyone. Let's get started. All right. So this is the second week. Okay, right. Let's go to Brightspace. Take a look at what's on the plan for today. I'm going to go to Content, Table of Contents. Okay, so we've covered these topics. So last week I introduced the syllabus. We just started talking about the basic ideas of the course. And we still have the PDF that I provided, so I think I went through some of the terminology, kind of finished. I'll start there today. And then we're going to cover today on the agenda, we have these two modules, essentially. All right, so we'll take a look at that. If I had to give this lecture a name, I would call it something like Embeddings from AutoEncoders to BERT, something like that, right? So that's what we're going to talk about. But this is actually pretty important because it ties in to training GPTs using BERTs to understanding how BERTs work, leading up to reinforcement learning, which is, a key concept. Okay. For those of you that took 520, BERT is pretty much the same architecture. I will cover probably next week just how I did baby GPT. I'll probably do a baby BERT kind of a thing, and you'll see it's pretty. We're not going to spend as much time on BERT, but I'll do at least that so you can see the actual code. All right, but today I'm going to lay the foundation. We will look at an autoencoder. It's a very simple concept, but it's like some of those ideas you can find in BERT as well. Okay, yeah, so I'm still working on homework one. Homework two will likely be the training a GPT via reinforcement learning. We'll start talking about that next week. Okay, be on the lookout for homework one sometime, by the end of this week. Okay, I'll post it, and then I'll talk about it probably next week. All right, yeah. So let's start here. So obviously we're talking about practical deep learning. As I said, deep learning, as I said last week, deep learning is a very broad topic. There's a lot of concepts there, but essentially it's like neural networks, with lots of layers, right? And when they become that big, because they have so many layers, then you need a lot of data to train them, and there's a lot of methodologies and techniques to training a model. So usually this pipeline goes beyond our standard training that we did like in basic machine learning courses. And now we have this sequence of steps, I should say, for training a model, which are called pre-training, fine-tuning, reinforcement learning. So this is the sequence that we might want to follow. Um, so those are the concepts that we will need to look at. Now, for this process, we could, of course, do it from scratch, but usually we have these very powerful libraries, right? And I introduced last week the library transformers from Hugging Face, right? So that we'll continue to use that. And they have frameworks, even more advanced frameworks, where you're going to apply reinforcement learning, for instance. All right, but let's start here with the PDF. So I gave you this paper. So take a look at it as much as you can. Today I'll talk a little bit about the architecture of the original transformer, just to continue to elaborate on GPTs and BERT models. We did a whole bunch of examples with Hugging Face just to see the capabilities. We were only in inference mode last week, so we did no training. We were just using the models as they are. Okay. And so that was these examples, and hopefully you started looking at Hugging Face and just see what's out there. So maybe some of you have gone to Kaggle in the past, I would imagine, right? For data sets, for code, Jupyter notebooks, things like that. Well, imagine, Hugging Face is similar to Kaggle, but for transfer learning. So it's got, really large models, and that kind of thing. All right, so I think we ended last week on this PDF, which is just really some definitions and terminology of transfer learning, right? So I'll kind of finish this up, and then we're going to move on into some of the ideas. So I think we covered probably this pre-training. We discussed that fine-tuning. Just consider that, pre-training is, training a model from scratch. So at that point, the initial weights are going to be random. And so you're providing that initial training. That's going to be a lot of data, right? The whole internet, if you're training a large language model, 10 million images, right? So that's the idea. That's called pre-training. Pretty standard. You use some normal loss function like MSE or cross entropy. Okay, so very similar to traditional machine learning, but it's the initial stage. After that, and we have fine-tuning. Fine-tuning is step 2. We take a pre-trained model, something that was trained, as I said, on massive amounts of data. Maybe it required 1,000 GPUs at least, right? And now we take that model, we bring it in, right? So, and now we continue to train. So we're going to take it from there and do additional training. And this, but as the name implies, is called fine-tuning. So that means we're just like slightly nudging things in one direction or another. Okay. This doesn't require massive amounts of data. So 100,000 sentence pairs could be enough. One GPU, can be enough, right? And so this is something that we will be doing a lot in this course, right? For your homework assignments or projects, you'll do some. We may actually do a little bit of fine tuning today, just at the end of the class, just to complete the pipeline or to show you the pipeline from beginning to end. Okay, without getting into too much of the details, but this is an important concept. So ideas here: you're going to freeze the weights, some of the layers, right? Or you're going to use a learning rate that is much smaller than the original learning rate, right? So all of these are essentially steps that you would take to fine tune. Again, the key thing is you trust the weights, but you just want to nudge them a little bit. And especially not the first few, not the weights of the first few layers, but you would want to change the weights of like the last layers before you actually predict something. And the intuition here is, for instance, in images, first you need to detect circles or even, dots, lines, curves, and then shapes, circles, and then eyes and things like that, right? So you build on what you did in the previous layer. And so you trust those initial layers are getting like the primitives that you will use for future inference. So yeah, so that's the difference between pre-training and fine-tuning. We will do very little pre-training here. I mean, today we might do some pre-training, but it's very tiny with an autoencoder, something like that. So pre-training here is just normal training. But fine-tuning is where, we're going to do more, right, just to see how we can change the behavior of our models, both for images and text. Keep in mind, as I think I've said several times, this idea of pre-training and fine-tuning hasn't made it to every field, right? So it's, this is very robust in like images, in text, but if you think of industrial operations, right, there's so much opportunity. I go to a factory, go to a plant, there's no pre-trained models for that. But imagine once you have a pre-trained chemical plant model, right? And maybe it uses time series data. So that's so if you've seen in the syllabus, we'll cover RNNs a little bit. That's actually sequence or time series data. So, and I'll show you a little bit of how, for instance, you could do a time series GPT, right? And so you can see where a lot of these ideas can transfer to other mediums beyond images and text. But for now, if you look at Hugging Face, it's going to be mostly images, text, some audio like speech, and a few other things here and there. Okay, so we talked about fine-tuning. I think I did this example of freezing the weights, so we covered that. Sharing the weights from one model to another, so this becomes an important thing. So if you remember, in PyTorch, we have this model.parameters that essentially is capturing the weights and the biases of the model. So sharing weights is very important as it allows pre-training to be done only once. After that, only some modification to the weights needs to be done, and in Torch, the weights can be extracted easily using, for example, the function model.parameters. essentially when you go to Hugging Face, that's what you're downloading. You're just downloading like a map of what the architecture of the neural network should be. You know, the architecture of the GPT, for instance. GPT-2, for instance, has similar to you know, like the original GPT decoder, but it has 12 layers, right? I think, or something like that. And so you have to take that into account, build that architecture, and then download the parameters that go with that model. Do you guys see that? So that's why, for instance, if you decided to do this, let's say you want a GPT written in C, you can do it, right? So just make sure that you get the architecture exactly correct as the original GPT uh, model that you're using is, and then download the weights and load them into memory. Currently, there are specialized libraries that help share models. These include Hugging Face's Transformers module and FastAI. We'll use FastAI later in the semester, much later, after the first exam at least, when we look at the image side of this, right? Images. Yeah. All right, so reinforcement learning through human feedbacks, or RLHF. I don't think I covered this one last week. This is a very important topic. So this one comes after fine-tuning. So you have pre-training, then fine-tuning, and then followed by reinforcement learning. So reinforcement learning is a field, it's a type of training technique. But this one, reinforcement learning through human feedbacks, is a very nice one because you use it when you don't quite know how to train the model. So when you don't know what loss function to use or how to write a loss function, you know, let's say you want to teach, like the example I gave last week, you want to teach a robot to dance salsa, right? This was the original paper of RLHF. This is how they motivated it. They had a simulation and a robot. How do you write the math equations for that? You don't know, right? But as humans, you know, we don't quite know how to create something sometimes, but we know how to, when we look at something, we know how to recognize what it is. You see, and so they came to this realization that, you know, let's have a model. It creates one, two, three options. Let's look at all three options and we can simply say, I think this one is better. So the other two are not as good. So you rank them and that information feeds back, right? So it's some kind of input that goes in and you get some score, some value. All right, so we'll learn how to do this. This is one of the main things that we'll cover, and you'll get an assignment. For this one, today I'll introduce GPT-2 that you can use for that assignment, just very easy to use with Hugging Face. And the Transformers module, but that's something you can use. Obviously, if you have more computing power, better GPU somehow, use a better model. GPT-2 is, you know, a few years old, so it's not that great, but it was trained on a lot of data. It's just, it's been a while, and GPT-2, the reason why I'm using GPT-2 is because in the demos, it'll run. If I bring something bigger, it may not run. Okay, so that's the idea. So let's go through the definition. So reinforcement learning through human feedback, RLHF, is a technique for reinforcement learning, where you train a model by providing feedbacks. Since manually creating the reward function to create feedbacks is very difficult, this can be done by replacing the reward function with another neural network. And that's one of the key things that we will learn, right? So for instance, you can provide, I'm sure, you know, a company like OpenAI, they hire experts to provide the feedbacks. But there's only so much that humans can do, right? If you automate a process, it's just going to be much faster. And so this is what they learned. They learned that they could, you know, collect some data of providing this feedback and then train a neural network to kind of simulate that behavior. And then they just used that model to provide the feedback to the GPT. So there's actually two models working together. Now there's a downside, obviously, you know, it's more space. Oh, yeah, go ahead. Yeah. Okay. Ah, okay. Yeah, so this technique, reinforcement learning, has a specific type of a loss function that provides like a contrast between what is good and what is bad. So you bring these two things and you use that information to update the weights of the model. But the, the thing is, you create this mechanism that is based on this contrast of either two or three options and knowing which one is better. And so the model needs to produce the one that is better. Do you see that? And that is so it's essentially an update of the weights. Okay. Sure. Yeah, it's got a memory and it has saved all of your conversations. That is only an inference time. So any communication that you're having with ChatGPT is inference time only. So that means it's not being trained on your data, but it has your data. And so it uses your data as context to the prompt. Do you see that? So it's like it can add all that information to whatever, tell me something about me that you have, right? So well, you're gonna say, then ChatGPT creates its own prompt inside, and it'll say, this is this person, this is what I know about them, and now I'm gonna say more things. And so it uses that and it goes into the model. But at some point in the past, it was trained to do that. Not with your data specifically, but with data like that, where, so essentially it would get a prompt, produce an output, and the procedure is to create two to three outputs. Do you see that? So it's like this is the model. It receives the question, and it produces one, two, and three. Then a person, like OpenAI, at some point hired people to look at the question, look at three answers, and say this one is better. That's reinforcement learning. You don't have to do it for every possible question and answer in the world. You just, as it turns out, just do it for a few. And so now that information is question, answer, 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 and we have a score for each one that says this is the best, this is worst. So now you take that information, there's another type of loss that is a contrasting loss function. Do you see that? So it's going to say, okay, now I need to produce, this answer, this is the good one. And so if it doesn't produce that one, then it penalizes the weight, so the error is higher. If it produces that output, the error is lower, correct? And so it's the same stochastic gradient descent mechanism, which leads into updating the weights. Do you see that? But the weights are updated based on that. Yeah. No, the weights are not being updated during inference time. That's, whenever you're using ChatGPT, it's in inference mode. Now it can reason in inference mode. But that's a different thing. That's it just like generating text until finally it gives an answer. But that's still inference time. Whenever you update the weights, that happens offline. Got it? Yeah. We're actually going to cover some of these things, so you'll see. So, and to answer that question, so I said that a person does it, but actually you can automate it and have a BERT model do it, right? So that will be the homework assignment that you guys will get. I provide an example, which is already on Brightspace, of spam generation. So I'll have a GPT that generates text, right? And what's my goal? To make it more spammy. Do you see that? And so now it's going to start generating text that says, blah, 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 win $1,000. Cash here. That's spammy, right? But the project that I give you guys is, that's the example I provide. Then you guys have to find your own like thing that you're going to do. So some students in the past have tried to make a model more toxic or less toxic, for instance, right? Do you see that? Which actually is kind of, you asked this question as well just now about toxicity, right? You can actually see that. You can make it more toxic if you want, right? And provide, because the BERT model can give a score to the text that's being generated, and if it's not toxic enough, it's gonna give it a low score. And once it, looks toxic, it gives it a high score because a BERT takes text, right? So it's like an understanding process of the text, but it only provides a score. Do you see that? So yeah. So these are some of the ideas. Any other questions? No? All right. Yeah. So good. Yeah. Reinforcement learning is, to me, it's like an amazing technique. It's the thing that actually made ChatGPT work. Like before, it didn't work. Pre-training was nice, didn't work. Fine-tuning was nice, didn't work. Right? You asked it a question, sometimes it was a totally random answer, right? But they fixed it like that. And that's, by the way, like the last time they told us what they're doing. After that, they've kept it a secret. People have to like kind of infer what they're doing because they don't reveal anymore. But this was one of the last things that is known, right? Reinforcement learning. All right, and the idea, as I said, came from the people in robotics, and things with images. But this concept can be applied to other things, time series data. You'll see later in the semester. All right, so let's continue. So as I was saying, RLHF is a technique for RL where you train a model by providing feedbacks. Since manually creating a reward function to create feedbacks is very difficult, this can be done by replacing the reward function with another neural network. In this case, if we're doing an LLM, obviously we need a neural net that understands text, right? And so that's why a BERT makes perfect sense. Okay. So for example, we can train a GPT model to generate more positive or more negative movie reviews. So we can totally do that. This process involves giving text prompts about movies to the GPT in order for it to generate text responses from those prompts, right? The basic mechanism. These generated text responses, movie reviews, and the original prompts are concatenated together and given to a reward function for evaluation. The reward function will assign a score to the input text indicating how good it is. The reward could be based on heuristic rules, human feedbacks, etc. A clever approach is to use a task-specific BERT model to read the GPT-generated text and assign a score, reward, given this text. As such, the BERT model can be used as the reward function, okay? Which is kind of what I've been explaining. As it turns out, this was an amazing solution. For some people still think is not enough. Some people still, even though it's amazing, some people still think it doesn't have enough power to take, to advance GPTs in artificial intelligence. Like some people think we need something else. But currently it's a really nice solution, one of the best solutions available. But there's also another problem. There's two models here. A GPT, which is really large, and a BERT, which is also very large. And now instead of just training one model, you have to train two models. Kind of similar idea to the GAN, right? You had a generator and a discriminator. Two models working together can be hard to train. Just as an aside, recently, a few years ago, Stanford University published a technique called DPO. By the way, a lot of these algorithms used and that's what I haven't talked about, like the optimization, It's a specific optimization set of optimization techniques called policy optimization. Okay, and there's been several variants of those, like GRPO, PPO, DPO, which is that Stanford paper. Um, yeah, so SPO. So there's many variants. Okay. But that DPO that came from Stanford University did some amazing math, almost like a proof, right? A math proof, and they figured out that they could rearrange all the terms to just have one model. So essentially, having a BERT and a GPT, they could get rid of the BERT. So there's that, okay? But in this course, I'm still covering both models. It's more intuitive. But yeah, that's also, that has happened. There's advantages to it. All right, so let's see. There's some performance metrics for transfer learning, so we'll look at some of them. I'll just mention them briefly. There's GLUE, a set of tasks that, like benchmarks that people would evaluate on. The BLUE score, for instance, is used for translation. So the point is, some of the metrics used now go beyond just traditional precision, recall, F measure, MSC, and things like that. Okay, if you're interested in these metrics, this is a great paper that you can take a look at. It's got a very long list of metrics. Okay. All right, and so that's some of the terminology that I wanted to cover. All right, and so you get the idea, sort of the terms, taxonomy, I guess, of transfer learning. Now, let's go back to Brightspace. Table of contents. We are essentially done with this module. That was our first module. That's covered. So we're going to move on to the second module, okay? So here I have some notes. So I'll go over those, and I have a code example. So we'll do an example. In this class, I kind of mix like just writing something from scratch with PyTorch, and then obviously when we need to use a big library, we'll use the transformers library. But these two topics are related. So as I was saying, if I was to give this a name, this lecture, a name, I would call it like Embeddings from AutoEncoders to BERT. But they're essentially the same thing. So that's what we're going to discuss. Along the way, I'll mention something called Word2Vec, which was great, and then it's just in the past because it has been surpassed by many other things, but it was amazing at the time. Okay, and so we'll talk about that. So here is the code that we will look at. We'll implement this on Colab, and it'll be your autoencoder. I'm thinking the homework will relate to this. Okay, so to pay attention to it. All right, so this is an autoencoder, actually. So this architecture, this network architecture, which is called an autoencoder, is the one that was used for Word2Vec. Okay, the Word2Vec algorithm, Word2Vec technique came around in 2014. Right? And it was invented by Mikolov, this person here, also at Google, probably. I believe he was at Google. All right, so here we'll implement something like this in code, but just take a look at this because it should be very strange to you, right? It's a neural network. It's got one input layer, one hidden layer, one output layer. Do you see that? The size of the neurons, the input, goes from 1 to V, where V is the size of the vocabulary. Okay? So that can be words like cat, dog, happiness, right? But we usually don't use, as you know, right? We usually don't use full words because, you could have happiness, happier, happiest, happily, right? But that's a lot of words. Or you could just have like the root hap and then, add the thing that changes it, right? Like happier or happiness, right? So that way you're more efficient in the way that you construct. You can construct even new words, like I gave you the example, iPhoning, right? So iPhoning, right? So, but anyway, so usually I think these large language models have a vocabulary of about 50,000 subwords. Okay? But if it's simpler to you, just think of them as words. Notice that this is implying that there's 50,000 words in the vocabulary and that this input layer has 50,000 neurons, one for each word in the input. And then notice over here that the output is the same, right? Word 1, word 2, all the way to word V. So the same, 50,000. So vector of 50 goes in, vector of 50 goes out. And in between, all you have is a hidden layer made up of size M, the number of neurons, which is not going to be 50,000. It's going to be much, much smaller, like 256 or 512. Do you see that? So what is this doing essentially? It's like a compression and decompression, right? So compresses, decompresses. This has been called encoder and decoder. You can see it's the same kind of terminology. This has existed for a while, this idea. But in 2014, Mikolov used this architecture and invented an algorithm that they call word-to-vec. Okay, we're not going to look at word-to-vec itself. It's kind of dated at this point. I can provide a link for you to look at, and you can implement it yourself if you'd like, the code. But it's better just to look at this idea of the autoencoder, and we can implement that. So let's talk a little bit about it. So essentially, what are you doing? You're taking a vector of 50, multiplying it times a weights matrix to produce a vector of 512. Then you take that vector of 512, multiply it times a weights matrix to produce another vector of 50,000. Do you see that? So that's the architecture, and then you use it in some way. So for instance, you could use it with this. So what is this, by the way? So this is a one-hot encoded representation in the vocabulary, right? So what that means is that we have 49,999 zeros and 1 1. That's one-hot encoding. But this is the way that we traditionally can represent the words in a vocabulary, right? So the one-hot encoded version. So essentially then what you can do is you can have any word connected to any other word. Do you see that? Right? And what you're going to do during the training is you're learning these weights to produce this thing in the middle, the hidden layer, which we can call the embedding. So that's where this embedding was starting to come from, right? So think of it as a way, instead of getting this data out here, you actually focus on just this layer. This is actually the thing that you want. So now you have a way of embedding things. So you give it a word, multiply it times a weights matrix, and now you get its corresponding embedding of size 256. So what do you think is better? Having 50,000, value vector where only one of the values is a 1 and everything else is a 0 as a representation, or to have this as a representation which is of size 256 and where it's dense, right? It's dense. So that means all the values, all 256 neurons have a value that has meaning. Do you guys see that? So this is a thing that everyone aspired to having. And so we're going to take a look at this in a second. But let me switch to the whiteboard just because there's one thing I want to do. So let's switch to the whiteboard. So when I was first working on this, I was using the one-hot encoded approach. And so, what that means is it's very sad, right? So I had, for every word, I had a vector of size 50,000. Imagine that. So imagine here I have like 20,000 words. Think of it, right? So it's 20,000 by 50,000, but most of it is 0. I once showed my work to someone, hey, this is my data, and they're like, it's all zeros, right? And so it's true, right? Because they were just, what you can see is very small, and it was mostly zeros. But this was also called the bag of words approach. right? And so this was the technique in natural language processing for a long time. It's not great. What people wanted, these are called sparse matrices. There was like a whole area of math for dealing with sparse matrices. People didn't want that. People wanted dense matrices where every column has a value. Do you see that? And so creating embeddings was really important in an efficient way. And so what you wanted was not a matrix that was 20,000 by 50,000 of mostly zeros. You wanted a matrix that was 20,000, because there's still 20,000 words, but of size 256, where every value, every column has a number, right? And it's dense and it has meaning. And remember, because it's a matrix of size 256, these are also dimensions in a vector space. Okay? Very important. Embeddings are actually representations of words in a vector space. Okay? So back in 2014, when Word2Vec was invented, it was like an amazing thing because now you could actually do math with words. Okay? There was a lot of, and you can still do that today. This is probably why GPTs work so well because, as you guys know, GPTs use embeddings inside. They just learn them inside. Before you learned them outside, if you will, because people were still thinking in the traditional machine learning approach, where you first wanted the one-hot encoded vectors, the bag of words, and then you would use those in a KNN or a support vector machines or something like that. But now GPTs just have everything within the architecture itself. Okay? So that's an important thing to consider. All right. Oh, yeah, go ahead. Yeah. Could be smaller, could be 100. These are just 256 is always a multiple of something related to the GPU, right? First of all, giving it more capacity is usually better. So 256 versus 512, I would say back in 2014 because of the GPU. But their intention would probably be to go to 512. Yeah. Way smaller, like 10. Yeah, go ahead. Yes, you're using semantic discernment of the model. Do you see what I'm saying? Because it's a vector space. Each one of those things means something, right? Like you could have a column out of these 256 ones that actually represents funniness somehow. You don't know this, right? It's not like you initially said, I'm going to create a funniness column. But the AI model, if it thinks it's useful, it's going to create it. Because all it's trying to do as it's training, right? It's giving inputs and outputs. It's trying to predict something. It's trying to find, these columns. It's trying to figure them out. So that's why you just give it the capacity. You give it 256 semantic columns or axes in the vector space. And then it is going to, create the ones that it needs. Usually, if time permits, you'll see in my notes that I'm talking about something called LSA, latent semantic analysis. So that actually is also the same concept in a simpler way. But that the whole idea is you're trying to discover these categories that words fit into, and they represent features in the vector space so that every word, think of it as a point in that vector space. So words that have to do with animals are over there, right? Because you have an axis about furriness, and you have an axis of four legs. Do you see that? This is something the machine learning model is doing. It's discovering it. And it's never going to label it as a four legs category. But if you studied it, you would start to see it. Wait a minute. As a human, I would call this a four legs category. Do you see that? It's all being done by it. Embeddings is one of the key features that makes all of this work, for sure. Because it's finding this meaning. Got it? Yeah. Yeah, go ahead. I would say the more you give it, the more meaningful it is. If you give it too much, like a million, then you're wasting space. So you want to be, you always with machine learning, you want to be like, you want to force the model to do a lot with very little. So you stay with something like 256, 512. But I think between 256 and 512, people would want 512. The limit in the past was GPUs, right? As the GPUs get better, what is it, 512? So 1024, right? So you can go to that. Yeah, go ahead. And also having a lot of data. Sorry?
Very danger of overfitting with that.
With which one?
Well,
Well, I mean, this is you're supposed to train this with a lot of data. So that's going to help out. Yeah. And I mean, this has worked because the original transformer had an embedding, you guys know, an embedding size of 512. And that was the original paper. And I know they've extended that now to, more than that, but not too much. It's not going to go to 10,000, I don't think. You know what I mean? So you definitely don't want that. And then remember that these models are trained with massive amounts of data. Yep. Any other questions, guys? All right, great. So yeah, so we're talking about embeddings, right? We talked about one-hot encoding. You guys get that you don't want this massive matrix of all zeros. First of all, you're wasting a lot of RAM memory. You can't do a lot of training. It's all zeros. It's bad in like so many ways. Instead, what you want is this compressed matrix of, to something 256. This is the term embedding. So the embedding idea was there. A lot of people knew instinctively that they wanted to do this, but the algorithm wasn't there, right? And so that's where Word2Vec came in. So let's go to the notes. As I said, I don't want to get into the specifics of the algorithm because it's a very clever solution, but I'll go over it. So you do see that we have a machine here, right, that we can train. We can train the weights to produce these. So let's just talk a little bit. So semantic vector spaces, right? That's kind of the title of this topic. I'm trying to get rid of this thing. Here we go. Okay. Let me actually. I don't need the one. Just move this. Yeah, here we go. All right. So semantic vector spaces. So the idea here is a vector space model, right? So you guys understand this. For instance, I want to represent people just based on age, weight, and height. I can do that, right? And what's going to happen is every person will be represented by a vector of size 3 with these values. And so I can have people that are very tall, and they're all going to cluster in one side. Do you agree with that? Like tall people would cluster, children would be over there, right? That's exactly the value of this. Now, I intentionally decide that these are the 3 features or columns that I want to use. The thing with embeddings is that you don't define what these values are going to be. Instead, you just say, I'm going to have 256 or 512. And then training will fill in these values, and eventually the columns have meaning, axes. Okay? All right, so that's the key idea. So here I have a little drawing, and it's kind of the same thing. So I don't even know what the features are, right? The axes, but you can see that a machine learning model, if it needs to classify these different kinds of balls, it's going to find a way to group them based on maybe something to do with the size. Maybe some are round. So you can see what I did here. Some of them are more round. These are smaller, right? Have these strange line, 1 line, 2 line. So like the tennis balls, but then you have white tennis balls and green tennis balls. So so they cluster based on features. So the algorithm needs to figure out, maybe it needs some color, it needs something about circles versus other shapes and so on. Okay, so we don't do it. the AI will do it, figure it out. And it's going to find, and it can create this vector space. You could say 256, but it turns out that it only needed a subspace of the 256, maybe just 20. So there is a 20 set of axes there that were important and the other ones weren't actually. It's up to it. Okay? But that's where that comes in. Latent semantic analysis was a technique way before, but it was sort of the same idea. You would use an algorithm and you would have like dots represent the element. In this case, it was books. So here we were categorizing things by type of book, for instance. All right, so now let's talk a little bit about, so that was kind of the history, right? Old techniques that, that were there. And then came word-to-vec, word embeddings and neural networks. Remember, this is they use an autoencoder, which is this neural network architecture. So as I said, the algorithm is here actually. Like if you have an interest, read it, right? So but I don't want to get into this because it's pretty long and it's going to take a long time. So, but go ahead and read it if you like. But let's talk about this topic. I want to move on actually to more like BERT and things like that. So word embeddings and neural nets, right? So word embeddings are another approach like LSA that allow you to place data in a vector space to discover relationships. Specifically, word embeddings look at and this is now word-to-vec really, how word-to-vec does it. So to create these word embeddings, you look at the co-occurrence of terms in a document. This is essentially how it was trained. They had this context window, they called it. So they had a target word and they had 2 words to the left, 2 words to the right. And so it would grab these little batches, and this is how word-to-vec was trained. So think of it now as, I bring in the center word and I compare it to the 2 words to the left, 2 words to the right. And so what it was learning to do, it was learning how to like group words within this vector space. You see that, and it created all these ideas, and I'll mention one of them that's really interesting in a second. Does this make sense? Do you have a question? No? All right, yeah, so that's the idea, okay? So you have this architecture. You can take any word and represent it as a one-hot encoded vector of size 50,000. So now you need an algorithm, and this algorithm of word-to-vec in simple terms would take windows, take a book, find a word, and then look at the 2 words to the left, 2 words to the right, extract that, and now you provide target word, and then 1 word, then another word, you do it. And doing that training created these embeddings that were capturing meaning about the co-occurrence of words. So for instance, Paris, France. Do you see that? So it would grab the word Paris here and the word France. Washington, United States. You see that? So it's capturing, it can start to capture information. It'll see that, whenever I see Washington, I see United States. Whenever I see Paris, I see France. You see, so it starts to do that because it's looking at and so you can see there's some meaning there, right? So you're always going to see certain words together. And there's certain words that never, or are not likely to occur together, right? So bagel and what? Supernova. Those two shouldn't occur together, but bagel and bakery should, right? Likely. We got some bagels at the bakery, so that might be within that context. You see that? So that's essentially the intuition. The algorithm came from that. And as it turns out, this machine was just creating representations of words, but somehow when you would put these in the vector space, they were together, okay? And they had actually a little bit of geometry. So, so I covered this, I covered that. So let's just go over word-to-vec briefly. So so I said this. So word embeddings look at the co-occurrence of terms in a document. Word embeddings have existed for a while. However, the improvements in deep learning technologies have led to the development of newer techniques for calculating these word embeddings. In particular, Mikolov, his paper, proposed new algorithms to calculate word embeddings. One of the methods he proposed was called word-to-vec. You can see the code below. Now, word-to-vec is just an algorithm that you use as is. The code seldom needs to be modified except for a few parameters. In particular, word-to-vec has been widely used for natural language processing. It takes a very large document set and produces a vector space where all the words can be mapped. The vector space is based on the co-occurrence of the words. The dimension m, which is the number of orthogonal axes in the space, is determined by the number of neurons m in the hidden layer of the neural network used to perform the analysis, right? So that hidden layer. There are various implementations of word-to-vec. The most common one is called a skip-ground model, and it uses a one-layer neural network to calculate co-occurrence of words. That's essentially the gist of it. As can be seen in the figure, it has these three layers. So the input layer consists of the words and the vocabulary of size v. So one-hot encoding, once again, is used here. For example, for the vector dog, cat, blue, that might represent a vocabulary of a total of 3 words, the word cat would be encoded as 010. So that's one-hot encoding. Okay. So the vocabulary defines the number of neurons in the input layer. These one-hot encoded vectors for the words in the vocabulary are the inputs to the input layer of the neural net. The outputs of the neural network are also the one-hot encoded word vectors using a softmax, as we know, so that we have a probability distribution of the most likely word. Remember, this will just predict something that adds up to 1, and it's going to compare it to whatever the real one is, and that's how it learns. You guys see that? So that's essentially the most simplified way of thinking about the algorithm. And then here's a representation of it so that you can imagine now every word, essentially you create now a representation of it, a vector of size 256. And these now, if you go into the vector space, become points in that vector space. Do you guys see that? Okay, so this was the initial, yeah, let's do that. That's going to work really great. Then they did some research and they found out a very interesting property in word-to-vec. So here it is. One of the important observations Mikolov et al. Made about word-to-vec space is that semantic relationships can be discovered by performing vector arithmetic. Okay, so think about that. We can probably do that also in GPTs. Okay, so for instance, given enough data, the following vector arithmetic may be discovered. King plus man minus queen equal woman. So let's think about this one, right? So this is let's go back to the whiteboard. So it's king plus man minus queen equal to woman. Okay, so again, this is from a paper. That's not even an example I'm making up. It's in the original paper. So they discovered this idea. So remember now, every word I'm going to use a 3-dimensional representation, right, just to keep it simple, of the vector space. But remember, this would be R 256. So it means there's 256 axes, yeah? Right? So now every word in here is a dot, okay? And so they said, okay, we can now do these things. Like, what was it? King. So it's king. What was it? Plus man. Minus queen. So you can see what it's doing. It's like reasoning, but in a geometric way. And they called it vector arithmetic. So woman. So essentially, it's like there's a point king, and then there's a point man. So these two vectors, adding them together, right, produce another vector, and then minus the vector that is woman would result, or sorry, queen would result in, let's say, king, man, and then that produces some vector. Then we have queen. It might be. It might be. So I don't remember, but it doesn't really matter. I'm not doing any math really. It's more symbolic than anything. So, but just think about it. So it's like you have this relationship, and then you have some kind of thing like this, and then it just tells you, well, the next position is going to be woman. Sorry. Do you see that? So something like this allows you to find another word that's related semantically. So another example that they did was they said, um, USA plus capital equal uh, Washington, right? So you could find the other position. So by that analogy, then they say, okay, if that works, let's do France equal capital, and what do you get? Paris, and and so on. So you can play with this idea, but you just have to do the math of this, and you could find it would sometimes maybe it wasn't precise, but the word was going to be around there somehow. Do you guys see that? So what this is saying is that not only was it like clustering the words, but it was putting structure in the vector space so that you could find relationships. Okay? So yeah, so this is so I'm trying to think like yeah, go ahead. Yeah. The training. Hmm. So you have a lot of data and you just feed it to the model. So you would feed, you know, king, queen, then king, castle. You feed that. And so the model gets an input, predicts an output, and you compare that output to the word that you gave it. You minimize that error, backpropagate, update the weights. Make sense? So that's the idea. Okay? But yeah, so yeah, this is something that was found in the paper. It was like proven that it worked, and it was really interesting. I'm not doing the actual math in this vector space, right? So you have to like use your imagination here. But um, they could, do these things, and they tried. I'm pretty sure things with capitals and things like that. Okay, so this is telling you that something additional is being captured in the vector space. All right, so I think that has been a good discussion. Okay, let's go back to the documents. Um, yeah, so as I said, one of the important observations Mikolov et al. Made about word-to-vec space is that semantic relationships can be discovered by performing vector arithmetic. For instance, given enough data, the following vector arithmetic may be discovered, right? So it gives you the word. Right, and then it just goes into the code of word2vec here, and so on. All right, so now let's switch gears, right? So we did here, we talked about Word2Vec, and we looked at the neural network architecture that is used to train it, which is essentially something called an autoencoder. All right, so that's what we're going to do next. We're actually going to implement in PyTorch a little autoencoder. This is not just for Word2Vec. Some of these ideas can appear in the GAN. Obviously, you're doing embeddings, so that BERT will use some of these ideas. Only BERT is based on transformers, so it's a little bit more complex. But actually, my example is yet another application of an autoencoder. Okay, so I'll show you in kind of, and it's not difficult to implement. So let's go ahead and do that. So I'm going to close this one here. I'm going to go back to table of contents. Get my PowerPoint. So let's go here. Here in AutoEncoder, so we covered the notes, we went over those ideas. Now let's take a look at implementing an autoencoder. And like I said, this is going to be probably your first homework assignment, just still working on it. This is the autoencoder that we're going to implement, and then I will, we'll discuss what we can use it for. Okay, so let's open up Colab. Okay. All right, so I'm going to add some libraries here. I'm using PyTorch, of course. We're building this one from scratch. Okay, so Torch, NumPy, OS, Torch Optim, Torch NN, Torch Utils to build a data loader, the tensor data set, and some Torch metrics. So let's click on that. So this also helps everyone to kind of see a little neural network from scratch, right? Oops. Torch metrics is missing. So we need to install that. Pip install torch metrics. All right, so that finished. Let's install the libraries now. Okay, here we are. Okay, so first thing, I'm just going to create some random data, okay, to keep it simple. So I'm using torch.rand, and I'm going to create a matrix that is 1000 by 784. So like MNIS, right? This should be familiar to you. If you remember, MNIS was 28 by 28 as a two-dimensional grid. So if you spaghettify it, it becomes a one-dimensional vector of size 784. So that's my data. Okay. Now, because I'm building an autoencoder, I'm going to use, in its simplest form, I can just use the same data for both input and output. And you might think, what is that good for, right? But if you remember what we were doing here, think about the architecture of Word2Vec. It wasn't necessarily the same data, but it was definitely the same dimension, right? So a vector of 50 as input, a vector of 50 as output. Do you guys see that? Here in my example, I'm doing a vector of 784 as input and a vector of 784 as output. Yeah? And I have 1,000 samples of data that I've just generated. So I'm going to take all the samples with all the dimensions, and I'm going to create X train and Y train. Okay? And that's the data that I can use to train this autoencoder. So now I'm going to use a train dataset and train data loader to just to load the data correctly. So I'm going to take X train, Y train as a tensor dataset, assign it to train DS, and then train DS is assigned to data loader, batch size 64, shuffle equal true, right? And that's the data. And now let's build the architecture. So I'll just copy this and talk about it. So we're taking the standard approach of creating a class. I'm going to name the class AutoEncoder. It's going to inherit the NN module from PyTorch. We're going to have two functions, an init function and a forward function. Okay? So this, we get the input dimension and the encoding dimension. No, remember that the input dimension will be the same as the output dimension, 784. The encoding dimension is whatever I want it to be. But that is what? Your embedding. You see that? So that's your embedding. So I initialize the autoencoder. And here, notice I'm going to create two objects, one called encoder, one called decoder. Okay? And if you remember from 520, we had two ways of creating neural networks. One was to go, X into F to create H1, and then H1 went into the next layer to create H2, and so on. Or we had NN sequential. And in NN sequential, all you have to do is put in as many layers as you want in sequence, and the data will go through those layers. So in this case, then, I have NN sequential. I have one layer, NN linear. What is NN linear? Matrix multiplication, right, between one input and the weights to produce the next layer. So I do NN linear input data, that's 784, to encoding dimension, which will be, let's say 100, and I have a ReLU activation function for that hidden layer. Okay? So then I have a decoder, and again, I'm using NN sequential. That's an NN linear from encoding dimension 100 to the output layer, which is the same as the input layer, 784. You guys see that? And here I have a sigmoid, all right? So that we can scale the data to be between 0 and 1, for instance. Okay? So this is not softmax. This is sigmoid. Keep that in mind. If I was using softmax, it would be more of a choose one category kind of thing. This is sigmoid modifying all the values because it's an image, right? 784 to 784 in this example. Does that make sense, guys? Any questions on that? No? All right, so I have encoder and decoder. And then now in the forward function, I just put them together. So X comes in, goes into encoder to produce encoded, which might be the thing I want to have as a representation vector. And then encoded goes into decoder to produce decoded, going back to 784. That's the architecture, in its simplest form. Okay? And that's really the hard part. Then after that, we just do the training. So this, again, to remind you of the training. So here the input dimension is actually 784. Well, I've been saying 32, so 100. So let's just make it 100. That's my embedding thing. Now, we've talked about how we can use it for word representation. So we're creating an embedding space right, for these values. But we can use it, we can think of other uses for it. Now let's take a look at, we instantiate the autoencoder, we providing input dimension, encoding dimension, that's our model. Then what do? We call the atom optimizer, and we pass to it model.parameters, right? As we train, that's the optimizer. The criterion, notice, is just MSE loss because these are like image values, so they're like regression values. And then we, for epoch in range 10, and then we just grab the data from train DL for x comma y, zero out the grads, provide x as input to the model. This gives us the predicted, right, vector of 784, and now we're going to compare that to the real vector of 784. Everyone with me? Yeah, and this is the same idea with word2vec. Really, the algorithm is about getting those words, right? But the mechanism is this. So you can see that was the simple architecture of it. And then we have a loss function. Once we have the loss function that compares predicted to the real, what do? Loss.backward, right, which calculates the derivatives. And then we use that information to update the weights. And that's it. So if I run this, there it goes and starts training. Okay. So we train it there. And that's an autoencoder, right? So that's an autoencoder with its own data. So what could we use this for, right? That's kind of the question. So here's an example. Whoops. Let's take a look. So this autoencoder is an anomaly detection system, I should say. This is an idea a friend of mine had some time ago, which I thought was really great. He suggested for network security, right? So you guys know that detecting something in the, like an attack in the network is really hard because you don't have enough data about attacks. But instead, you can flip the coin by not detecting the intrusion, but detecting or knowing what the normal behavior is and then finding anomalies. You see that? So that's what, that the idea that you create autoencoders for the protocols of the network. So you create a SSH autoencoder and a, HTTPS autoencoder and another one, HTML autoencoder, right? So you create all these where you know the normal behavior, right, of a sample. So the idea here is you take whatever the thing is, right, as a vector that goes in, and it's supposed to reproduce, to create an output that is similar to itself, right? That's what this autoencoder is doing. Input and output are the same. Do you see that? So it has train and embedding in between, a weight matrix, that's supposed to get an input, and the output should look similar. But his idea was, well, when we get something that is an anomaly, it's going to go in, it's going to be converted, but it won't be as close as it should be because it was originally an anomaly. So it doesn't follow the original distribution that I know. Do you guys understand? Any questions about that? So this is an anomaly detection system. Yeah. So you have 100 samples of what SSH looks like, right? So 100 examples goes in, it's the same, and in here it's learning, right? To always produce the input as an output. For that distribution of 100 things that it knows to be SSH. Then comes in an attack. Well, the attack is different somehow, goes in, comes out, but then this one is a little bit, is more different than the others. It wasn't able to reconstruct it as well, if you will. Okay, so then how do you measure that? You can measure that by calculating the distance between the input and the output, right? Because they're both of the same dimension, 784, which means they're points in a vector space. Do you see that? So this is the idea with the anomaly detection autoencoder. So actually this has a use, even though it seemed like it didn't. All right, so let's think it through with some examples. So here I have three ideas just to kind of illustrate this. I'm using random data, obviously, but so here would be one example, right? So now I've trained the model to recognize SSH. You see that? And so now I create just one input of size 784 called sample 1. I can print the shape of it, which will be 1,784. Sample 1 goes into model to produce res1, like the reconstructed version of it. And now you just take the pairwise Euclidean distance between the two, what went in and what came out. The idea being, if what came in is from the original distribution, then what comes out should look a lot like it. That means the distance between the two should be, 20. Now, something else comes in that is not like that distribution, which means it's different, goes into the model to produce an output. When you take that distance, it's no longer 20, it's 25. So now of all the values that you have, you rank them. The one that has the highest value is the most, what? Anomalous. The most anomalous. All right, so let's take a look here. So this is definitely going to give me a value, which is 29.16. Okay, again, I'm using random data, but bear in mind. So now I have that value, 29. So I'm going to take, I'm going to do a second example. Again, another vector, random, of size 784, sample 2. It goes into model to produce res2, right? It reconstructs it, if you will. And now I take the distance between sample 2 and res2, and notice, okay, this one is also around 29. So, but, this one's a little bit more different, I suppose. And then try yet another one. Uh, 784, sample 3 goes into model to produce res3. Take the Euclidean distance between the two, and this one is 28. So now if you look, you have 28, 29, and 2916. So if you rank these three, you can identify the most anomalous. And that, it's a perfectly valid, privacy preserving, see how fancy it gets really quickly. It's a privacy preserving anomaly detection system that can be easily implemented in a network with just good data. You can go sell it if you like. You know what I mean? It's true. I mean, it's like a pretty good solution actually, and it's very simple. And you can create. All you have to do now is, instead of creating one single thing that detects all the attacks, you actually build individual little anomaly detection systems for every behavior that's normal. SSH packets, HTTPS packets, right? Or something like that. And then they're all working in the background, scanning packets, but they're all being scored and ranked. And the top one is going to pop up and you can take a look at it. Yeah. And that's an autoencoder, so we've seen these ideas of creating embeddings, so remember that, right? So you saw me here. I have, so just kind of let's go to and we'll take a break in a minute. So kind of to summarize this autoencoder, because I'm going to move on. But remember, this will be homework 1. I'm still working on it. So let me just kind of summarize this one here. Okay. Right, so we built an autoencoder, and it was like this, right? So the vector is size 84, because I was thinking like images, but this can be just about anything. I built a hidden layer, which I think I did 100 neurons. And then this was also 784. This is similar to word to vec, except that word to vec was 50,000 here, if you remember. This one was 256, I believe. This one was 50,000. You see this, they're very similar. Now, in word to vec, this word and this word are not the same, and that's actually where the algorithm comes in, right? That, it gets these words that co-occur in text. Like with this, center word, 3 words to the left, 3 words to the right, and it just feeds them as pairs, and then remember, input goes in, predicts an output, compares to the real, takes that different, back propagates to update the weights. That's how machine learning works. So in this example, these words are different but co-occur. In the autoencoder example I just did, same architecture, but the logic changed a little. I just said, actually, this is the same vector, right? So, let's call it input 1, and this was also, even though it's output, it was the same input 1. So I was really training, right, to find these weights, right, that I give it a vector times this, right? It produces a hidden layer, and then that hidden layer times another weight matrix to produce the same thing. Like if I had an image of a cat, then I should get the same image of the cat. Okay? So then you might say, what's the application of this? Well, there could be an application for the embedding, first of all, like a compression at least, right? But I'm not even talking about that one. Instead, we're talking about an anomaly detection system, right? So the idea being a vector goes in, and it should produce a vector that looks like it. But if this vector is somehow anomalous, not part of the distribution, what comes out is not as good a reconstruction, if you will. So now when you take the difference between the two, it's a bigger difference. And that allows you then to identify it as more anomalous than other things. Make sense? All right, great. So that's autoencoders. Hopefully that concept made sense. But remember, we're still in the realm of embeddings, right? We still need to talk about embeddings a little bit more. So I'm done with autoencoders for now. We're going to move on to another embedding topic. But let's take a 10-minute break, okay? So it's 7:57. So let's come back at 8:07, okay? And we'll continue with the discussion.